Now we're going to look at some models of carbohydrates. So instead of using the handheld ball and stick models, I decided to use a 3D rendering software for chemistry called ChemDoodle 3D. The reason I chose to do this is because, quite honestly, the models did not translate well to video. So I thought this would be a better way to show you a 3D rendered version. They're much neater and much easier to understand. The only thing you have to know about these models is that these gray balls right here, these gray ones, these are carbons. The manufacturer has decided to give the background, to make the background black. So they had to choose a different color for the carbons, and they chose gray for the carbons. But that's the only difference. Everything else is the same. Red is still oxygen, and white is still hydrogen. All right, so this is a molecule of glucose. Now, here is the six-membered ring. Here's the oxygen in the ring. 1, 2, 3, 4, 5, and there's carbon 6 right over here. This is the anomeric carbon. And as you can see, this OH group here is going in the downward direction. So this is an alpha glucose. On every carbon around the ring, there is an oxygen. So there's an oxygen here, oxygen here, oxygen here, then the CH2O there. So this is alpha glucose. Now, let me do a little bit of magic here. Oops. Here we go. Now this is going to be beta glucose. Let me just get them out of the way here. So this molecule here, the one over here, is exactly the same as this one over here. Exactly the same. Except if we look at the anomeric carbon, the OH is going up. So this is beta glucose. So this is alpha glucose. The OH is going down on the anomeric carbon. This is beta glucose. The OH is going up on the anomeric carbon. So you're going to want to draw these in your data sheet. You don't have to be Rembrandt or Picasso. Just do your best and make me believe that you examine these structures closely and that you kind of have an idea of what these sugars should look like. All right? So that's glucose, alpha, and beta versions of glucose. Next thing we'll do is a molecule of maltose, two glucose molecules bonded together. All right? I'll see you then. Okay, class. Here we are looking at a molecule of maltose. Maltose, again, is two glucose molecules bonded together by an alpha 1,4 glycosidic bond. So now, here, let me see if I can highlight it for you. Here is one of the molecules of glucose, and here is the other one. Notice I didn't highlight this oxygen here, because that is the oxygen that bonds them together. This oxygen actually comes from this sugar molecule over here, but that's not really important for this class. So what I want you to do is I want you to draw this molecule into your data sheet as best as you can, and I want you to put special emphasis on this bond right here, the glycosidic bond. This is an alpha 1,4 glycosidic bond. Now, how do I get there? Well, in a carbohydrate, let me see if I can rotate this without making a mess of it. In a carbohydrate, here I am just kind of rotating it. There we go. In a carbohydrate, the glycosidic bond is basically an oxygen that connects two sugars. And in the six-membered ring carbohydrates, you have the anomeric carbon here. This is the oxygen in the ring, pardon me. The anomeric carbon is right here. The oxygen in the ring, the anomeric carbon, so this is carbon 1, carbon 2, carbon 3, right there, carbon 4, carbon 5, and carbon 6 is back here outside the ring, okay? So this is carbon 1. So the anomeric carbon is carbon number 1. The glycosidic bond is attached to it. So one of the numbers in your description of the glycosidic bond should be 1, because the glycosidic bond is on carbon 1 of one of your sugars. On the other sugar over here, this one over here, this is the anomeric carbon, carbon 1, carbon 2, carbon 3, carbon 4, carbon 4. So the glycosidic bond here is between carbon 1 and carbon 4. That one, carbon 4. So this is our glycosidic bond. Let me highlight it real quick. So the description of this glycosidic bond needs to include the numbers 1 and 4. So it's going to be something dash 1 comma 4 dash glycosidic bond. Now what goes before all that? Well, the direction of the anomeric carbon. Is the anomeric carbon's oxygen pointing down, which it is here, or is it pointing up, which if it was pointing up, it would be something else, a different sugar, a different disaccharide. Here the anomeric carbon has the oxygen pointing down. That's alpha. So this is an alpha 1,4 glycosidic bond. All right? Now in your book, draw this as neat as you can. Again, we're not expecting you to be Picassos or Rembrandts. Just do your best and convince us that you have examined this sugar closely and kind of have an idea of how it should look. Now let me do some 3D fun and do some rotations for you so you can kind of get a better look, maybe give you some different views of this molecule. Let me see if I can give you the top view. So there it is kind of from the top. And let's go back the other way and give it a spin. Oops, see if I can get it, just see if I can get it to spin. There we go. I spin it just because I think it looks cool. There are the oxygens right there. There's a different look. And back to where we started as best as I can. There, that's more or less where we started. And we'll let it rotate a little bit. It just looks cool. I'll stop it in the position where you probably should draw it, just because it'll make it life a lot easier for you. And let me see if I can give it a little bit like that. There. That's kind of where we started from. All right, so go ahead and draw that in your book, label the glycosidic bond and describe it. And that's the end of this part. And we'll move on to the next part, which is polysaccharides, much more complicated sugars. All right, guys, we'll see you then. All right, class. What we're looking at right now is a portion of a molecule of amylose. Amylose can be thousands of glucose molecules long, so I've truncated it down to only 4. But what happens is these 4 monosaccharides that are linked together, or this tetrasaccharide, if you will just repeat itself over and over and over again, going out this way over here and going out this way over here. Okay, it's all the same. It just keeps going to the left and to the right. And of course, it coils onto itself and does all kinds of interesting secondary arrangements. But let's focus right now on just these 4 monosaccharides, these 4 sugar units. I want you to notice, and the big take home here is, first of all, everything here is glucose. Every sugar is glucose. And every sugar, if we can see it, is put together by the same type of glycosidic bond. The same type. You'll notice it's the same glycosidic bond that maltose has, the alpha 1,4 glycosidic bond. All of the glycosidic bonds in a molecule of amylose is alpha 1,4. Okay, so this is a portion of the molecule amylose. Now, as you can see, it's only 4 sugar units long, 4 monosaccharides long. This example that I've given you. Remember, it's thousands of glucose bonded together. So if you think this is complicated, imagine what it would look like if there was thousands of them. Just incredibly complicated molecule. Now, this is a 3D rendered computer-aided visual. In reality, these molecules are not rigid like this. They're always moving. They're always undulating and finding the least energy they can be in and all this kind of stuff. They're always moving. But we're trying to give you a nice look at it so you can learn something about its chemistry. Now, let me see if I can make this bad boy rotate in 3 dimensions for us, just to give you a look. So there we go. So there's just a different look at the ring system. Again, here's the oxygen in the ring, right here. That's the oxygen in the ring. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So the glycosidic bond is on carbon 1 of that carbon. On the second sugar, the oxygen in the ring, anomeric carbon, so that's 1, 2, 3, and carbon 4. So here's the second carbon that's involved in the glycosidic bond. So again, it's an alpha 1,4 glycosidic bond. Now, you're going to want to draw this in your data sheet. I know it's busy. I totally respect that. It's a lot going on. But as always, I don't expect you, and nor do I think anyone else does, to be a Rembrandt or a professional artist. Just do your best with what you have here. And don't forget, you can always pause this video if you need to have more time. All right, so that is your look at amylose. We'll move on now to cellulose. I'll see you then. All right, class. Now we're looking at a molecule of cellulose. Now, cellulose and amylose are very similar. They're both made of glucose. But there's one very subtle difference that makes them completely different in terms of properties and structure. But the difference is extraordinarily subtle. Let's take a look right here. Let me see if I can circle it. There we go. There's the glycosidic bond. Let me circle it on this one. See if we can make it a little bit nicer. There we go. There's our glycosidic bond. So let's take a closer look at that. So this is the oxygen in the ring right here. There's carbon 1. Now in amylose, carbon 1 would have the oxygen going this way. But now if we look in the down position, there's a hydrogen there. This is a hydrogen atom right here. Going up from the anomeric carbon, you'll see the oxygen is going in the upward direction. That's a beta position. Everything else is the same between amylose and cellulose. They're the same, except for the position of this glycosidic bond. The fact that the glycosidic bond is beta makes cellulose completely different. It has different chemistry, different biology. In fact, humans can't digest it. That's how different it is. Amylose and amylopectin, its cousin, we rely on for energy. But cellulose, we can't digest at all. Isn't that interesting? Just that one subtle little change made it completely indigestible in humans. Cows and horses, however, love it. So there you go. Now, let me do some computer magic here and rotate the molecule for you. There you go. Now, if you like any one of these orientations better than the one I've shown you originally, feel free to pause the video at any time and take a look at it from the angle that you like. Let me give it a spin, just because spinning is fun. There we go. Kind of cool, huh? All right, let me get it back to where I originally started from, which was right about there. Kind of right there. And let me fix one thing right quick. They'll leave it. It's fine. Let me rotate it a little bit better than this, though. It's not a very good look. And it's the problem with these 3D software. Sometimes they're hard to get back to where you started. Anyway, there you go. If you don't like this look, just rewind this YouTube video and go back to where we were before. But this is cellulose. The difference between cellulose and amylose is the alpha-1,4 glycosidic bond, and amylose is changed to the beta-1,4 glycosidic bond in cellulose. But both are still made of glucose. All right, guys, and that is the end of the cellulose part. We'll see you soon. Hey guys, let's continue on with our experiments with carbohydrates. Now we're going to do the hydrolysis of a polysaccharide. I've got 2 test tubes filled with starch. Let me grab them for you. There you go. As you can see, starch is basically more or less a cloudy type suspension. It's just kind of how they look. So as you can see, that's what they look like. So now we're going to add acid to one, water to another, and we're going to do what's called a hydrolysis reaction, or we're going to see what happens when we do a hydrolysis reaction. So let's do that. So here is my 3 molar hydrochloric acid. I'm going to add that to the one labeled acid. I think it says 3 drops. So I'm going to do 3 drops. Actually, it's 5 drops. There we go. So there's the one labeled acid. Give that a little shake. And now I'm going to add some water to the one labeled water. Just going to use a squeeze bottle for that. 5 drops, best I can. There we go. That's about 5 drops. A little more than that, but that's okay. And now I'm going to put them into the, as you can see, they haven't changed much. They really didn't change at all. I'm going to put them into the hot water.
And I'm going to let them sit there for about 5 minutes, 5 to 10 minutes. 10 minutes, it says. So there you go. Let's let them sit there for about 10 minutes. Let's crank that up a little more, get the water to boil. All right, guys. See you in 10. All right, guys. It's been about 10 minutes. So let's take our samples out and let them cool down for a few minutes. Okay, guys. Now that our samples have cooled down a little bit, here's what they look like. After heating them, they got a little clearer. There you go. They're more or less comfortable to touch. So now I'm going to do a pH test. I'm going to take a piece of pH paper, which tells you the pH by color. And I want the pH of this acid solution to be above 7. Or to be 7 actually would be ideal, but if it's a little bit above 7, that'll be okay. So let's dip it into here. Now this most definitely, let me get on frame here. This most definitely should be acidic, right? Because, you know, we added acid to it, right? And there, as you can see, it's red. Red is right around pH 2, just so you know. So this is acidic. So now I'm going to add some sodium hydroxide to counter that, to make the pH come back to about 7. I'm going to add a couple drops. It says in the book to add a ml. I'm just going to add a couple drops. See what happens. 1, 2, 3, 4, 5. How about 5 drops? Probably going to regret not just adding a ml, right? Always follow the instructions, as they say. Sorry, this video seems like it's getting a little dark. Kind of doing these things last minute here, so bear with the production quality. He says like he can make it really good anyway, right? So let's try this again. Here we go. Still acidic, so let's add some more. I just added a boatload, about a half mil. I added about a half mil, to be honest with you. I'm going to stir it up a little bit, get it nice and homogeneous. And let's check. There you go. See, now it's blue. That's basic now. I've went a little higher than pH 7, but that's okay. That's okay. We'll be okay. Now, at this point, we want to get a sample of each one. So now I'm going to take a spot plate. I'm doing the iodine starch test on page 114. I'm going to take some of the one labeled acid. So let's put an A over here, and then we'll put a W here for the acid and base. Let me get my other camera adjusted here, guys, and I'll show you what I'm doing.
Okay, class, now that we've taken our samples of starch and treated it with acid and treated it with water and then heated it for 5 or 10 minutes, we're going to try to see what the result of our experiment is. In well number 1, this well right here, we're going to put our starch and water solution. So let's just put 5 drops in there. 1, 2, 3, 4, 5. This was the starch treated with water and heat. And we're going to treat it with an iodine solution. Now this iodine solution will turn black in the presence of starch. Here's what the solution looks like on its own. It's kind of a yellow color. Okay? So that's the solution on its own. Let's take a little drop and put it into the iodine solution. Now, as you can see, it instantly turned black. Instantly turned black. And that is very positive for the presence of starch. So starch plus water plus heat equals no reaction, essentially. Basically, you get starch back. Now, I'm going to take 5 drops of the starch solution treated with acid. 1, 2, 3, 4, 5. This is the starch solution treated with acid. Let's go ahead and put a drop in there, see what happens. There we go. And as you can see, it did not turn the same color. It stayed the yellow color of the iodine solution. So that tells me that there's no starch present in that sample. So think about it for a minute and try to determine what must have happened when we added the starch to the water and heat, starch to acid and heat. What must have occurred in that flask? All right, guys, I'll let you think about that. Write it up in your data sheet, submit it to your instructor, and presence of Benedict solution. So now we're going to test our starch digestion, the acid in starch, to see
if there's glucose there. So let's do that experiment right now. I'm going to add a milliliter of Benedict's reagent to each one. So here's my acid. Here's my test tube that's labeled acid. I'm going to add about a milliliter of Benedict's reagent to it. Let me get rid of this bottle here. Get that out of the way too. About a mil. It doesn't have to be too accurate, but about a mil. All right, so put a milliliter in here. And then put that back in the water. The water is nice and hot, so this shouldn't take very long. I'll make sure my other camera's picking that up. All right, very good. That's about a mil. Put it into this is the water one here. Okay, guys, that's the water. Water and starch together that we heated up for 10 minutes to near boiling. All right, let's put that in there. All right. Here we go. Let's just sit and wait now to see what happens. The glucose is definitely turning brick orange or brick reddish orange. That's a positive test for glucose, so that's really kind of cool. The acid solution in starch, after heating it for about 10 minutes in near boiling water, the starch digests it into glucose molecules. And then the glucose molecules we confirmed using a Benedict's test. The Benedict's test for glucose told me that this is most definitely a digested starch with glucose present. Isn't that kind of cool, guys? All right, guys.